Today we are continuing the discussion of multi-qubit systems and tensor products, and then we get started on projective measurements. So we've talked a little bit about measurements, like what we get, how to find the probabilities, but there's also the issue of what happens to the state of the system after the measurement. So we try to put that on a more kind of rigorous mathematical footing. So just to review again, the idea of multi-qubit systems was that we have a bunch of qubits, so I can have two, maybe A and B, or I can have three, A, B, C, maybe I have more, etc. Right? So this is a system of 2 qubits, a system of 3 qubits, and a system of 4 qubits. And the general state of a system like that will live in a space of dimension 2 to the n, so n qubits. Here, the basis states essentially for me are going to be 0, 0, 0, 1, 1, 0, and 1, 1. And implicitly, I've picked some ordering. So 0, 0 really means 0 of A, 0 of B. This means 0 of A, 1 of B, etc. So I've picked an ordering. And then, each of them can be 0 or 1. There are n possibilities, so there are 2 to the n basis states. In this case, I'm going to get, well, A can be now 0, and then BC can be any of those 4 configurations. So 0, 0, 0, 1, 1, 0, 1, 1, or A can be 1, and then I get all those configurations. 1, 1, 1. So there's going to be 8 different states, and then 8 different basis states, and then the state of this 3-qubit system can be written as a vector of length 8. Similarly, this becomes like 16 basis states. Sometimes it's useful to change that order that we've picked. So for example, let's give an example, right? So suppose we have a state let's say it's alpha 0, 0, 0 plus beta 0, 1, 0 plus gamma 1, 0, 1, maybe plus delta 0, 1, 1. Right, so that's a particular state of 3 qubits. And let's say the order that I've picked is ABC order. So sigma A, sigma B, sigma C, where each of these can be 0 or 1, is the representation of these basis states. So that means 0 of A, 1 of B, 0 of C. Okay. So if I want to write that as a vector of length 8, well, how would I write it? So I should have 4 zeros and 4 non-zero elements that are alpha, beta, gamma, delta. So let's see what they are. So the ordering is how these are ordered has this structure, you see. So we go from, let's say I only have 0 and 1, then first I put 0 and then 0, 1, then 1, 0, 1. Now I have those 4. I arrange all 4 of them with 0 coming first, and then 1 coming next. So the structure of the basis states essentially follows the rule of tensor multiplication. So something like, imagine to get all 4, I can do 0, 1, and 0, 1. You imagine like a tensor in this structure, it gives me this 0 comes with 0, 1, and then 1 comes with 0, 1. So that's the order, and then we have the AB the AB indices. So for 3 qubits, again, we just wrote the order. So 0, 0, 0 is going to be the first one. So this psi can be represented as, so I have an alpha here. The next one, so what is 0, 1, 0? So where does that go? 0, 1, 0 is the third one. So there's going to be a beta here. I don't know what I have here. There's a beta here for the third one. 1, 0, 1. What is that? 1, 0, 1. It's number 5, right? Sorry, number 6. I have 1, 2, 3, 4, 5, 6. So 4 and 5 I leave out. And then I put a gamma. And then that delta is 0, 1, 1, which is number 4. So that's delta. So now I have a delta here. So these appear at position 1, 3, 4, and 6. So then 7 and 8 are 0. Similarly, 2 and 5 are 0. So let's put the zeros in the right place. Okay. So that's in this ABC basis. Now, suppose I tell you write that state in ACB basis, right? So write the same state as, let's say, an 8-dimensional vector in ACB spaces. Okay, so let's go back to our state. For concreteness, let me put all the ABCs here. ABC. So let's look at the same states. Let's see what that is in ACB. Okay, so I switch the C and B, which in this case doesn't matter. 0 of A, 0 of C, 0 of B, plus 0 of A. Now C is 0. B is 1. And that thing physically describes the same state. I just like picked a different way of ordering my qubits. But these two are states where A and C are 0 and B is 1. So again, we're switching B and C. So A, 1C, 0B, delta, 0A, 1B, 1C. Okay? So that's the same state. So now its representation as an 8-dimensional vector with the ACB ordering will be different, right? We'll have these alpha, beta, gammas at different places. So alpha, that's like the first state, we said. 0, 0, 1 is going to be 0, 0, 1, I believe, is the second. Yeah, so that's the second state. 1, 1, 0, what is 1, 1, 0? Going back here, 1, 1, 0 is number 7. And 0, 1, 1, I believe that should be number 4. Yep. So that's 4. So then in, let's say, sigma A, sigma C, sigma B basis, the same state is I have alpha, I have beta, then a 0, then a delta. So that was number 4, 5, and 6 are 0, 7 is gamma, then I have a 0 here, right? That's a different representation. So it's kind of useful to have that in mind, that there's some choice that has been made about the order of these states. Okay. Now let's think a little bit more about this measurement business, so called projective measurements, for reasons that become clear pretty soon. So these measurements essentially project a state. In other words, the collapse of the wave function happens by projecting it to the space that's consistent with the result of the measurement. So we talked about measurements like in the case of just 1 qubit. So going back to 1 qubit. So I have a qubit and I perform a measurement on it. That's the notation that we'll see later, like when we draw quantum circuits, measurements are like a clock type of thing. So what does that do to the state of that qubit? So suppose before the measurement, pre-measurement, if I have a state alpha 0 plus beta 1, the post-measurement state, well, we said if I measure 0, then I'm guaranteed to measure 0 again if I measure immediately after. So that means any weight in 1, any probability of getting 1 goes away. So here I'm getting just the 0 if we measure 0. And that, of course, has a probability of alpha squared, absolute value alpha squared. So with that probability, if I have this pre-measurement state, I'll get 0. But once I get 0, my state just gets projected to 0. And then if I measure again the probability 1, I will find 1 again. So here, let's say for 1, Again, I projected state 1 if we measure 1. And then probability of that is beta, absolute value squared. Okay. So that's for 1 qubit. It's a simple case. But now imagine we have more qubits. So again, kind of, if we measure everything, it's pretty straightforward. So again, if I have, let's say, state alpha 0, 0, 0, 0, alpha 0, 1, 0, 1, 1, 0, 1, 0, so this is like a 2 qubit state, plus alpha 1, 1, 1, 1. So what is the fate of that state after the measurement? Well, and suppose we're measuring both of them. So it's a situation where I have measurement on both qubits. So let's say they both come in and they both get measured. Well, this should go to so let's do a table here. State, result. So if I get 0, 0, my state just gets projected to 0, 0. If I get 0, 1, the state gets projected to 0, 1. Similarly for 1, 0. And so this is 1, 0 and 1, sorry. This is the result, so I don't need to put the cat around it. So 1, 0, 1, 1, 1, 1. Then the associated probabilities are absolute value, for example, alpha 0, 0 squared, etc. Now we can think a little bit about, and these states are normalized, right? I'm picking just one of the states, so there's only one non-zero coefficient, that's 1, so the sum of the probabilities is 1. Suppose now I do a partial measure. So still I have multiple qubits, but just measure one of them. Or a subset of them. Maybe you have 5 qubits and you measure 3 of them, or something like that. So that's the most general case. Let's start with a simple example of just 2 qubits. Again, the same state. So let's say instead of measuring both of them, let's say I just measure the first one. So I have a situation like that. So I measure this, I don't touch the other one. Okay. So if I measure 1 qubit, the result is going to be, and I have the same state, right? So that's my state here before the measurement. The question is, what do I get? What happens to the state of the 2 qubit system after that measurement, depending on the result of that measurement? So in this case, if we call them like AB, I'm only measuring qubit A. So if we call them AB, and this is AB, 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 AB. If I only measure qubit A, okay, so there's going to be 2 results, right? It's either 0 or 1. So again, let's do same type of table. So state after measuring. And this is going to be like result for A. So A, if I measure that 1 qubit, there are two things that can happen. I find 0 or I find 1. But now, if I find 0, then that means that those states, like these two states here, these two states that have A equal, these two states that have A equal 1 here, they give some probability of finding 1, right, in a measurement. So they cannot appear in the post-measurement state of this 2-qubit system. So the measurement projects out these states that give rise to a finite probability of finding 1 out of that state. So I just found 0. So it tells me that these two things cannot be in the quantum state. These two, 0, 0, and 0, 1, are both consistent with 0. So I want to just make the minimal change to them. So somehow I expect my state to look like alpha 0, 0, 0, 0 plus alpha 0, 1, 0, 1. But then we realize that this is not normalized, right? So before the measurement, what added up to 1 was this quantity, right? So I have alpha 0, 0 absolute value squared, 0, 1, 1, 0, 1, 1. That sum is 1. So this is just part of that sum. So these cannot be the probabilities. Similarly, in the 1 qubit case, or in the 2 qubit case, measuring both, I did not write alpha 0, 0, 0, 0 because that wouldn't be normalized. I just put 0, 0 because I know that's normalized. So essentially what we need to do is to renormalize that state. And in order to do that, well, it's easy to see how we can do that. So we want sum of the squares of these amplitudes to be 1. So if I just divide that whole thing by the square root of alpha 0, 0 absolute value squared plus alpha 0, 1 absolute value squared, we can verify that that sum is 1, right? Because essentially what I'm getting, the absolute value squared of the first term is going to be absolute value squared of alpha 0, 0 divided by alpha 0, 0 squared plus alpha 0, 1 squared. The second one is going to be alpha 0, 1 squared divided by the same thing. So that sum clearly becomes 1, and that's a normalized state. So that's the minimal change that we can make to the state without messing up the normalization, yet projecting out any component of that state that would give rise to a finite probability of getting 1 for qubit A. And that's the recipe for changing the state upon a projective measurement. So the state 1, now if I measure A and get 1, it's again a similar story. Now these two, 0, 0 and 0, 1 will be inconsistent with that measurement outcome. So I need to project that out. And then my state after the measurement is going to be alpha 1, 0, 1, 0 plus alpha 1, 1, 1, 1. The whole thing divided by square roots, those numbers at alpha 1, 0 quantity squared, 1, 1 absolute value quantity squared. So that's the recipe for getting a state if we measure a subset of our qubits. All right, so let's work out an example. Example. Consider states, let's say psi to be some normalization. So you have 0, 0, 0 plus 2, 0, 0, 1 plus 1, 0, 1 plus 2, 1, 0, 0. Something like that. So that's for 3 qubits with, let's say, ABC order. So the qubits are called ABC, and that's how they're arranged. So this is 0A, 0B, 1C, for example. Okay. So first, let's measure qubit C only. So then we want to find probabilities and post-measurement states. Right? So we have this situation, A, B, and C come in and we perform a measurement only on C. Don't touch A and B, and that's the initial state. So so if I measure only C, there are two results, like 0 and 1. So let's see what we can say about the probability of getting 0 and 1. And then after we get either 0 or 1, what happens to this 3-qubit state? Okay, so first maybe we should figure out what that n should be. So this state must be normalized. So sum of squared of probabilities must be 1. So that means n squared times 1 plus 2 squared, which is 4 plus 1 plus 4. That's 10 is 1. So n must be 1 over square root 10. Okay. So that's our normalized state. Now, we measure C. So let's say result of C measurement, and then let's say probability, and then say post-measurement state. So we said C can be 0 or 1. It's just 1 qubit. So if it's 0, what is the probability? Well, there are, out of these 4 states in the superposition, there are 2 that are consistent with 0. So this and that give me 0. And then this and this give me 1 for C. So essentially, the probability of getting 0 for C is the sum of probabilities of everything that's consistent with having C equals 0. So that becomes the probability of this one, which is 1, which is n squared, essentially. So that's 1/10, plus the probability of this one, the other green one, which is 2 squared over 10. So that's going to be 5 over 10 is 1/2. Okay, so that's good. And of course, probabilities should add up to 1. So this must also be 1/2. And we can verify. So it's going to be the sum of these orange ones. Again, 2 squared over 10 plus 1 squared over 10. That's also 1/2. Okay, so we're good with probabilities. Now let's see what we can say about the post-measurement state. So if I find C to be 0, right, these two orange states should be projected out. They should not remain in the superposition. So my state looks like 0, 0, 0 plus 2, 1, 0, 0. And then the whole thing should be multiplied by some normalization factor. And we know what that is. So I have a 1 here, I have a 2 here. So I have to divide by the square root of 1 squared plus 2 squared. So that's the square root of 5. So that's my normalized state. Similarly, if I measure 1 for C, then these two states that have C equals 0 should go away. So I'm left with 0, 0, 1, or 2 times 0, 0, 1 rather, plus 1, 0, 1. And again, the normalization will be 1 over square root 5. Okay, so that's an example where we have 3 qubits, we measure 1. Let's say we now measure 2, and we want to see what happens. So is there any difference which ones we pick? Yeah, I think I'll maybe pick AC. Okay, so let's say we measure AC. A and C. Okay. So it's something like this. So let's write the state again. And I get rid of these colors. They were only relevant for measuring C only. All right, so if I measure A and C, this one has 0, 0 for A and C. This has 0, 1. This has 1, 1. This has 1, 0, right? So it seems all 4 states that we can get, we actually do get. So let's say AC measure, probability, post measure state. So A and C again, I'm reading off. This would be 0, 0 here. This would be 0, 1. This is 1, 1. This is 1, 0. So if I find 0, 0, there's only one state that has 0, 0, right? These all 4 have different ACs. So that probability is going to be just n squared, which is 1/10. Now 0, 1 corresponds to this state, so that's going to be 2 squared over 10. 1, 0 is that one. A is 1, C is 0. So that's also 4 over 10. 1, 0. And finally, 1, 1 will be this one. That's 1 over 10. What happens to the state? Well, in this case, it's kind of simple. If I get 0, 0, there's only one state. So I have 0, 0, 0. If I get 0, 1, there's only one state. 0, 0, 1. 1, 0, there's only 1, 0, 0. And 1, 1 is only 1, 0, 1. Okay. So that's measuring two of them, A and C. Let's consider another case. So let's measure A and B now. So if I measure A and B, leave C alone, actually, I can replace that with 1 over square root 10. We don't need to keep writing n. Okay, so I'm measuring A and B. So the things I can get are 0, 0, right? If this one has 0, 0, this one has 0, 0, this has 1, 0, that has 1, 0. So it seems out of the 4 states that I can get, I only get 2. So let's say the result for AB. So it can be 0, 0 or 1, 0. So that means if I want to worry about the other possibilities like 0, 1, and 1, 1, they have a probability 0. So there's no states that we can talk about if the probability is 0. But then what about 0, 1? So what's the probability of, sorry, what's the probability of getting 0, 0? Well, for 0, 0, we put an orange sign here. So 0, 0, 0 corresponds, we're looking at A and B, right? So these two states. And 1, 0, there are now these two states that are consistent with it. So here and here, right? The first two are 1, 0. So the probability again for 0, 0 is going to be 1/10 plus 2 squared, which is 4 over 10, 5/10, 1/2 again. Similarly for this, I'm getting 1/2. Post measurement state. Here, there's nothing. Here, what am I getting for 0, 0? Well, I have to pick these two. So 0, 0, 0 plus 2, 0, 0, 1. The whole thing must be divided by square root 5, right? 1 squared plus 2 squared is 5. And for 1, 0, I have these two. So I have 1, 0, 1 plus 1, 0, 0. Oops, plus 2, 1, 0, 0. The whole thing gets divided by square root 5. Okay, so we have some idea of how to deal with measurements and partial measurements and figure out the probabilities of various results and figure out the states after the measurement, where any part of the state that's inconsistent with the measurement outcome we just saw gets projected out of the state. So one thing that may be illuminating to discuss is, like, we viewed these like 2-qubit measurements as like a one-shot process. We measure at the same time. But what happens if we measure one first and then the next? So we can kind of go back and first, like we discussed, just measuring, let's say, just measuring C, right? And then I talked about measuring AC, A and C. So suppose I really break this up. I think of measuring A and C as first measuring C and then measuring A. So let's revisit the AC measurement as first measuring C and then measuring A. So if I first measure C, we analyze what happens. That was the story there. Now let's say we take each of these cases and we measure A only. Okay? So if I take this state, so let's say measuring A on post-measurement states after measuring C. So there are two possibilities, right? So one of them is 1 over 5,000 plus 2,100. So 1 over square root 5 2,100, right? That's the state over here. Yep. So if that's the state, then measuring A gives me, if sigma A is 0, with probability, it's just this one, 1/5, I get that. And then after that, my state becomes 0, 0, 0. If I measure A to be 1, that's the probability 2 squared over 5. So that's 4 over 5. And my post-measurement state is going to be 1, 0, 0. Okay. So see, this is like the probability of getting 0 in measuring A if I have that state. That state itself was obtained with a probability a half, right? So the total probability of ending up here, namely first measuring C to be 0 and then measuring A to be 0, is going to be 1/2 times 1/5. So that gives me, let's do this for the other state and then we put things together. So the other state was, if C was measured to be 1, that's 2,001 plus the other one is 101. Now, if I measure A again, I can get 0 or 1. 0 occurs with probability 4 over 5. 1 occurs with probability 1 over 5. And these are conditional probabilities, right? If I have that state, which means if I did get 1 when measuring C, And then this gets projected to 0, 0, 1. This gets projected to 1, 0, 1. So putting things together, looking at it this way, so AC, I can have 0, 0, 0, 1, 1, 0, 1, 1. Probability is going to be, I had 1/2 for each of those cases. So 1/2 times 1/5 is 1/10. 1/2 times 4/5, 4/10, 4/10, 1/10. And state, again, is 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1. So that's the same thing, hopefully, that we got when we analyzed the AC measurement, right? That was here. Yeah. 0, 0, 1, 1, 0, 0. Did I mess up something here? So AC, I think AC is 1, 0 here, it's 0, 1 there. So you write the correct state here. So A is 0, C is 1. That's going to be this case, 0, 0, 1. And A is 1, C is 0. That's that case, 1, 0, 0. All right. So we see that there's consistency in this measurement. I can kind of, if I'm measuring a subsystem, I can view that potentially as measuring parts of the subsystem and then putting things together. All right, I think that's a good place to stop.